today we're going to be doing something a bit different. I have already proven the theorem for today. Instead, we're going to be generalizing it. So this video is going to be about digits, specifically sums of digits and qualities between the two. I've proven one of the theorems already for base 10, and we're going to be generalizing it to arbitrary bases. I figure this is going to be a good balance between me trying to struggle and, the video taking way too long. I think the previous two videos have been a little bit hard to watch because I spend a lot of the time just like trying to figure out how to approach the problem, and that's not exactly perfect learning material. So before we get into it, I'm going to explain the existing theorem, how to use the lemmas, and some of the basic lemmas that I'm using in the standard library, just so that you guys are on the same page. So if you already have experience with working with digits and digit sums, then feel free to skip the first part of this video. All right, let's get into it. I'm going to go over the existing theorem that I've already proven. We've already generalized this one, so let's start with that. This is a theorem that says that the sum of the digits, so this is the list of the digits of n times b, is equal to the sum of the list of the digits of just n. And the reason is because when you add, when you multiply by the base, you are adding a 0 digit in any base that you're in. And so that means that the digit sum is not affected by that. Okay, now I think this is only true for bases that are greater than 1, though I don't think you can do this in base 1. I haven't ever worked with base 1, so I wouldn't know, but pretty sure you need to at least, well, let's see real quick. Does this work? No, because this requires, So we're using, most of the heavy lifting is done by this lemma in the standard library, and this is one of the good lemmas to know when working with digits. And it's that the multiplying by a power of the base, and this is a bit too general for what we need, but that's okay, is the same as appending that many zeros at the end of the number, right? So that's the list.replicate k0. And this append is actually at the beginning of the list because, and this is also important to understand, let's just do a quick eval here. Let's do 1, 2, 3, and then we'll do base 10. So the digits of 1, 2, 3 in base 10 is 3, 2, 1, not 1, 2, 3. And that's because digits is defined as being in little endian order. So the most significant digit is last and the least significant digit is first. And you might think, like, why would you do that? It makes a lot of sense actually with functional programming, because most of the time when you're working with lists, you're going to be working with the head of the list. And most of the time when you're working with numbers, with digits, you're going to be working with the least significant digit, whether that's with induction or whatever other kind of proof technique you're using. Usually you start with least significant. Okay, so how does this work? So first thing we do is we say by cases on n, and that's just to make it a little bit easier so that we have positivity of n. Obviously, if n is 0, then this is true because 0 times 0 is 0. Otherwise, if n is positive, now we can apply this lemma. So we can say that we have 0, a single 0 appended to the digits of n, and that's the same as the digits of n times b. And basically, this is just by simplifying the existing Mathlib replicate lemma. So we get, after we use the Mathlib lemma, we get list.replicate 1, 0, and then simp will take care of that replicate. Actually, we don't even need to simplify the replicate. It's reflexively equal to, since it's a function, it's reflexively equal to the goal, right? So we can say exact this at this point, and that closes the goal. Just to clarify that a function that evaluates to something is reflexively equal to that something in lean, because refl and exact that runs refl for you, they are computing the value of the function. They're computing the actual value and fully simplifying the function if possible. Okay, so once we have that, then we're almost ready to finish. We do cases on n. I'm not sure why you would need to do cases on n here. Let's see if we can get away with just rewriting the digits. That's a little bit weird why I had that there. So we rewrite digits mul base, and then we get this expression. And then simplification will take care of that. We can do that in one step if we wanted to, and then we're done. We can also do this a little bit more elegantly. Instead of, I like to have my by cases have 2 dots all the time. So since this doesn't really fit very well, I mean, it does, but I like the look of it better if we said we have positive n and we have positive, or well, n not equal to 0 really is what we have here, not positive n. And actually, if we just said positive n here, that simplifies the part where we use it, because then we can just say this whole thing is positive n. It's a bit cleaner. And how are we going to do that? So we're going to say that it suffices, and this is super common, you have to know how to do this. It suffices to show that n is not equal to 0 by, and I always use library search here because it always works instantly. And now we've converted the goal from positivity, an inequality, to a not equals. And this is very, very important to know how to do, because a lot of proofs are super easy to do this way. The idea is you convert it to a not equals, then you introduce the equality, and then you substitute the equality. And that will simplify everything everywhere and make it super easy. So in this case, we have a problem here because I don't see the original goal. And so in this case, I don't think we can actually do this unless we do like some kind of by contraposition to get the original goal. So that's okay. We'll just go back to what we had. We can say, no, instead we'll just say by cases. So by cases of positive n, and when we have n not equal to, here we're going to have not 0 less than n. So we're going to push the negation at positive n, and then we're going to simplify. What happened here? Oh, I see. So we're going to change our suffices to a have, because we have n not equal to 0, and we have that from positive n. Maybe we don't. Oh, I see. We have n equals 0 from, and I believe there should be a library. Yes. Okay, so now we know n is equal to 0, and then we can just simplify with this. So that just saves us a little bit of work later on. Oops, no, it doesn't. Shoot. Okay, so we have to say, it's a little bit of a weird way of doing this. Let's do a little bit more normal way. We'll push the negation through at first. So we'll say n is less than or equal to, say n is less than or equal to 0, right? And push neg. And I'm getting so off topic here. Okay, let's finish this up. So now we have, yeah, this makes more sense. Okay, right. So that's that. But what I really wanted to go over today was the sum equivalence. So I already proved an equivalence between the range of 10 to the n plus 1 and 10 to the n cross, the cross product of the Cartesian product, sorry, from 0 to 10. So the proof technique is very straightforward. We use sum bijection, and this says that if you can give a function that can be inverted, that you can prove that it's invertible, you can show an equivalence between two sums. And in this case, the bijection is with a mapping x to the pair of x divided by 10 and x mod 10. And the reason is pretty straightforward, right? Because any number can be expressed as itself divided by 10 along with the remainder of 10. And this is true for any base. And then vice versa, we can go back from this by simply multiplying by 10 on the left side, on the left part of the pair, and adding the right side to get back the original number. And so this proof is pretty straightforward. We pretty much each time we're going to simplify a thin-set into inequalities. And then once we have the inequalities, you can see here thin-set gets rewritten into inequalities, and then we simplify the successor power. So n plus 1, we have to simplify that into n times, well, 10 times 10 to the n. And after that, it's just omega. Omega needs a little bit of help with the successor of power, but once you get rid of that, it usually doesn't need any help. Here, we don't even need to simplify anything except at the beginning, I guess. And then omega takes care of everything. Here we have to give the actual number that we're going to use that's equal to j. And that number is the 10 times j, and j corresponds to x divided by 10, obviously, and k corresponds to x mod 10. And if we use 10 times the left plus the right, then of course we can prove that we get back the original number. And so that's what we're proving here, along with some other stuff, but mostly this is the key part of the proof where we say that, where we say here that, no, I had it right. So 10 times j plus k divided by 10 is equal to, it's a little bit weird. I'm not sure exactly why this is all divided by 10, but yeah, whatever. It's the same thing. In the last one, we just basically prove something that is a very basic building block of working with digits and division and modulo, which is the standard library's div add mod, which says that any number is equal to some number times itself divided by n plus the number divided or modulo n. And this is basically the core of this whole proof, right? Like you can consider this entire summation equivalence a more abstract version or more complicated version of just this simple statement. And so that is no surprise that it's part of the proof at the end. Okay, so how are we going to go about generalizing this to any base? So I think I've already filled in this one. Yeah, okay, so we're going to say this is true for any base greater than 1. And I left the positive b here. We'll get rid of that at the end if necessary, but I left it up to check at the end if we actually need the base greater than 1, but it will help to have this during the proof so that our tactics and library search are more effective. So let's get right into it. So I've already converted this to, I've already copied this, all of the 10s into just base. And I prefer this syntax when base is a variable. This does not work with 10, by the way. You'd have to put 10 in parentheses. But if it's a variable, you don't have to do that. So the digits of I from 0 to b to the n plus 1 is the same as, why do I have oh, right. This p stands for pair. Okay, so how are we going to go about doing this? So in this case, omega has a lot more trouble, and it's not surprising because 10 is it's a finite number, but we don't know exactly what b is. So how do we prove here that x divided by b is less than b to the power of n? Well, we should have that this equation is, we should be able to divide both sides by the base. Right, so we should be able to say we have this by g conger. This does not work because it's you have to be a little bit careful when you divide both sides of an inequality. You're allowed to divide both sides of a less than or equal, an inequality that could be equal, but you're not necessarily allowed to do it all the time for a strict inequality. And the reason is, of course, is because when you've defined division, natural number division, like they have in Lean, in the Lean standard library, that any remainder is simply ignored. Well, it's chopped off. I don't know what you would call it. I don't know what the technical term is, but the remainder is discarded. So that means that 1 divided by 2 and 0 divided by 2, for example, are equal because both of those become 0, evaluate to 0. So the inequality of 0 less than 1 is not true if you divide both sides by 2 with natural numbers. So if that's the case, then it follows, logically speaking, that we would have to prove that both sides of the inequality are divisible by what we're trying to divide by. So in this case, we would have to show that x is indeed divisible by the base. And we don't have that. So in that case, we can try to do by cases on that and then solve it in the case. Maybe we'll learn something in the case where that's not true. So we'll say by cases, b divides x, and we're going to say b backslash bar x. In the first case where this is true, we should have simply by library search, right? And in the case where this is not true, b does not divide x. We can try to do something. I'm not sure this is even possible to prove. Let me see. In the other theorem for base 10, how would we go about proving this for base 10? So let's try to do a library search here. So we get the same library search. I think it's the same, right? So we had div lt of lt mul, div lt of lt mul, right? And it's using xin. So, okay. So this should still work. So it's interesting that it didn't. And what I said was actually false earlier. So apparently, if the right side of the inequality is multiplied, is divisible by n, then you can divide both sides by n, even if the left side is not divisible by n. So I learned something new every day. Okay, what about the next part? So here we need to prove that if I mod b equals j mod b, so let's put a mod eq here. I guess I didn't introduce everything here. Mod eq. And you know what? Let's do the same thing preemptively. We'll do a library search, see if we get something. I don't think there's going to be anything here. It took too long. Let's see. We need to prove that I is equal to j. All right. So if I mod b equals j mod b, then I should equal j. Yeah, this is very close, right? Like clearly the only thing that could mess this up is like probably if I or b or something is equal to 0. So that means this is a good candidate to do apply on, because apply will be, we should be able to find a lemma that almost, but has to prove something like j equals, j is greater than 0 or something like that. Unfortunately, we don't see anything like that. So it's possible I mod b equals j mod b. If two numbers have, oh, sorry, I'm not thinking about this very well. If two numbers have the same remainder, then they don't necessarily have the same value. But if they have the same, if b divides both of them, I mean, if I divided by b equals j divided by b, and then the modulos of b is equal, they should be equal. So how can we express that, right? Well, I think what we have to do is we have to use the same lemma that we did in the last part. So we'll say we have this, and this is going to be, we'll call this I eq, and then we'll have one for j. So we'll call this j. And now we're going to have two equations for I and j that use numbers that we have in our hypotheses, right? Expressions we have in our hypotheses. And now this is a really good candidate for trying omega, because maybe omega could figure this out. Unfortunately, it can't. So instead, we'll just rewrite everything, right? So we'll rewrite I eq and j eq. Now we should be able to rewrite, actually we should be able to simp all here. Yeah. So the reason why we can simp all, so I'll just do this in one step. Oh, okay, never mind. The reason why we can do this with simp all is because simp all is going to take these equivalences, and basically every time it sees an I, since I is always on the left side, we're going to be rewriting all the i's into j's, and then we're just going to have two equal expressions. So that's done. So how about this one? So this one is 3 expressions. So we're going to use split ands instead of constructor, because we have 3 goals, and constructor can only do one and at a time, and then you would have a nested constructor. So I'll just put in 3 sorries to start. We have to prove, in the first case, b times j plus k less than b to the n plus 1. Okay, so let's just try omega, because that seems pretty easy. Of course, a power is less than that. So maybe if omega doesn't work, we can help it out a little bit with this. Still can't do it. Okay. Okay, so then let's start thinking about this a bit. So we know that k is less than b, then we should be able to say it suffices b times j plus b instead of k. So let's try that, unless I got this wrong. Well, I'm gonna say omega here. Okay. great. I didn't get it wrong. Good. So now we should be able to say it suffices, and let's see if we can do this all in one step. B plus 1 without this B. No, okay, we couldn't do that in one step. Fine. No problem. We will do it in two. So let's see if we can do this one first. And this is going to be by simp add mul, I think, in the opposite direction. Rewrite. So small add. So just add this. Be in the other direction. Oh, cool. Okay. So I don't necessarily want to do that though. I want this simpler expression. I don't want the more complicated one. But then that doesn't work. Okay, we'll just use 2 suffices then. Sure. Why not? This doesn't need omega. Wait, really? Okay, simp A maybe? Simp using this. Okay, fine. Suffices. This might be tricky because we don't have positivity, but I guess we do. Cool. So, okay, so the problem is that when we had a strict inequality, we were a little bit, we wasted information a little bit, right? If k is strictly less than, then we can replace, on the left side, we can replace k with b, but we can actually go one step further and say, transform the goal into a less than or equals to. And the reason is because if k is strictly less than b, then the kind of equivalent to k on the left-hand side is b minus 1. So b minus 1 works, as does b, but b minus 2, for example, doesn't. And of course, the smaller the left side is, the better for us because it's easier to prove. The larger it is, the harder it is. But a less than or equals is better here because then everything factors, right? If we had a minus 1, that would be tricky to use. We want to keep everything divisible by b. And that way we can say we have j less than b by exact, I think. Yeah, perfect. Okay. So this is a great example of a proof where it seems you have to do everything correctly. Like you have to take the correct approach. You can't just replace the left-hand side with something. Even if the tactic omega works, that doesn't necessarily mean that you've done the best possible approach. You've taken the best possible approach. The best possible approach fully uses all of your hypotheses. And of course, sometimes that's not necessary, but in this case it is. We have to use the fact that k is less than b. It's not enough to just use the fact that it's less than or equal to b, which means when we replace b with k, when we replace k with b, we have to also either subtract 1 or, and in this case, it's much better, instead of subtracting 1, to say, okay, it suffices to show less than or equals, okay? And obviously the relationship between less than and less than or equals is a difference by 1. Okay, it's also a good example of, how using suffices can really make a goal easy to work with, or a proof easy to work with. All right, so now that was the first case. Now we have to prove that this is equal to j. So this is not an inequality, but it seems like we might still want to use the same thing here. And so I'm just going to take these two and I'm going to put them up at top level just so that I have access to them everywhere. Oh, I see. I can't put them up at top level because I don't have all of those variables. Okay, so in that case, we'll just copy them over here. Oops, I'm not sure I need I, but just in case, I don't even have an I. Okay, yeah, we don't need it then. All right, so let's rewrite j eq. And I'm going to say, instead of rewrite, I'm just going to say substitute j eq maybe. And then let's give it a simp. That did not work. Okay, wow. So I see the problem. So there's j on both sides, but clearly I want to rewrite it on the right side, not the left side. So to do that, we use convert and left-hand sum. So if we, this is the equivalent to just regular old convert with a LHS, a single application of LHS, and then that writes it. Oops, I got my left and right confused. This is the right-hand side, and then it only rewrites on the right-hand side. Okay, so then I think we need to do a rewrite of adddiv. Right, nat.adddiv, maybe? Yeah, okay, so now we have an if then else. So let's do this with simp simp doesn't work if you are missing hypotheses. So add div takes an additional lemma of positivity. So we need that b is say pos b. Okay. Does that give any other goals? No. So we can do simp now. And now we have ifs. So if you ever have an if, then you use split ifs. That gives us two goals. The first goal is usually pretty easy to prove. Oh, I take it back. Okay, sorry about the change in theme. I had to take a break. Okay, so where we left off, we had this problem. We were trying to prove this equation, and this is true because after you distribute the b, k divided by b with natural division is 0 because k is less than. So we can prove that with a few extra lemmas. First, we have to show that k mod b is less than b, and actually not sure why I showed that. So at the end, we wanted b times j plus k. We should just, let's do this in a more straightforward way here. This should be div nat.div mod, or sorry, div add addition is first, of course. Oh, right, okay, yeah, okay, so we did the add div, and it's giving us this if statement, right? And I think I said if you have an if statement, you can use split ifs to handle each case. In this case, actually, no pun intended, we actually don't want to do that, right? And I'm just going to give the positive b here to get rid of that second goal. We don't want to handle either case because otherwise we'd have to do a proof by contradiction. That wouldn't be fun. We know that b should be less than or equal to this. Let's try to prove this, right? If you can prove the positive or negative truth value of an if statement, then simp with that proof will handle, it will simplify the if statement. So in this case, we're going to try to prove that b is less than or equal to b times j mod. And we're going to prove this by showing that it suffices to show the positivity of j mod b, right? Because we can divide both sides by 1, or by b. Exact. Oh, wait a minute here. What's going on? Right. Okay, so this is b mod j. Yep, okay. So b mod j in parentheses, b mol j, b times j mod b is, of course, not necessarily divisible by b, right? So instead of doing that, we're going to prove kind of the opposite here. And that is that k mod b is less than. Now, oh shoot, I didn't even notice this. This is b less than or equal to this whole expression. Okay, so I did kind of an interesting proof here without even knowing it. Basically, all we had to do was say that one side of this, let's put this back, that this side, k mod b, was not greater than or equal to b. And then once you showed that, then this if statement is still not true because it doesn't matter what this term is, whether it's positive or not, doesn't change that truth value. So I did that by showing first that k mod b is less than b. Of course, this is true, trivially, and that's with this mod lt of lt. It should be even more trivial than this lemma, I think, but I'm too lazy to find exactly what that is. You know what, actually, I'll show you how to find it exactly right now. So we're going to clear klt, and then we'll do another library search, and this should still be true even without klt. Oh, no, because it's a strict less than. Strictly less than means that you do indeed need a proof that k is less than b. Otherwise, this isn't necessarily true. So for example, 10 mod 10, not less than 10. What? No, that's still, when would it be the same? I can see why that wouldn't work, but okay. Point is that after we do add div with the split, we split into an if statement. Sorry, we don't actually split. We get the if statement, and then we simplify the if statement with our not k mod b greater than or equal to b, and this becomes the goal. And now all we have to show is that b times j divided by b is indeed j, and k divided by b is 0. Now, simp can't do the rest of this. Omega can't, or maybe simp all can. Oh, okay, simp all could. But I'm going to show you how to do it very surgically. right? So clearly there should be a lemma in the library that says b times j divided by b equals j, and there is, but we can't find it with library search until we simplify this expression. So we'll do that first, and we're going to do that with rewrite with the show tactic. So we're going to say show, and this is how we can specify the type for a tactic. So we're going to show the type that we're going to specify is k divided by b equals 0 by, and then we're going to use exact here because that's also going to be in the library because we know that k is less than. This might need a proof that k is less than or equal to b. No? Okay, we found it. Great. And then after we rewrite that, we're going to change, so actually instead of rewrite, we're going to change this to simp. And that way it'll get rid of the 0, the plus 0. And now we're all set to use our library search, and indeed library search finds the correct lemma. Great. Okay, we only have one left. So the last goal, let's see how hard this is. B times j plus k mod b equals k. Okay, clearly this is true, right? B times j mod b is 0, plus mod b should be k, right? Now, all we need to show is that modulo b distributes over addition, right? So let's see if there's a library lemma for that. B times j mod b plus k mod equals k, was it? Let's do exact. So once again, this is going to be too complicated for library search. So how do we simplify it a little bit to make it possible for library search to use it, right? And what we're going to do is when you have a suffices, the goal that you're giving the suffices, the new goal by default is called this, right? So, and you can actually name it if you want to. I don't care right now, but you can say like this colon equals colon not equals, and then whatever the new type is going to be. But right now we just have this. And so what we're going to do is we're going to convert to this, and that way that will get rid of the equals k, and then we'll just have to show that these two things are equal, and hopefully library search will be able to do that. If it can't, it's probably because my math is wrong and not because library search is not working. So we'll just say convert this. And now convert did too much work, so we're going to say, okay, just do one step. And that one step is to get rid of the equal sign. Now, this is a bit extra, this is a little bit extra steps, right? We could have just said rewrite this, okay? That would have worked too. But, you know, then we would have to convert on the right-hand side instead, because now you can see this is converting the left-hand side too. So we'll just say convert. Convert this using 1 or 2 or whatever is a very general method of solving this kind of dilemma. Okay, now we're going to try a trusty library search. And does not look good. Okay, so, okay, we'll try omega. If omega, yeah, okay, so omega doesn't work. Yeah, I'm thinking that this is not necessarily true. The last thing I'm going to try is suppose that we have b divides b times j. This might be the missing thing that we need. If we know this, does this become true? Actually, if we have this, we might not even need to use the suffices. Like, we might just be done with the goal entirely. So let's check that that does not work. Okay, we'll say omega. Okay, and I'll try simp all. Simp all. Wow, look at that. Simp all came through. Okay, so the trick was to first set this up, right? Actually, I should have tried simp all to begin with. We did not even need b divides b times j. Simp all was able to just do this. Can we just do simp here? Okay, it's just simp alone was able to do this. Okay, so that was kind of silly on my part. Let's see what lemma simp is using. Okay, mul add mod self left. Okay, and this is just saying exactly basically what we need, that a times b plus c mod a equals c mod a. Okay, great. In that case, we just need to prove that k mod b is equal to k, and of course this is true. Very trivial. Okay, done. That was not as hard as I expected it to be, which is good. Let's tidy this up a little bit. I like having a little extra spaces on the long proofs here. All right, so this is a proof. Oh, and look at that. I almost forgot. we don't need the fact that the base is greater than 1. This was very helpful of Lean to just be able to tell me, even though I'm using all these simple and everything powerful tactics that use everything in scope, Lean still was able to tell me that that was not necessary. So that's great. Okay, so this is true for any positive base, even base 1, which I did not know or think was possible. Interesting. Okay, I guess the reason is because we're not using any kind of replicate 0 here. This has not using the same, that we did in base mul digit sum, where we were really leveraging the digits base pal mul lemma. All right, so now we have to use this in our, we're going to rewrite our more specific lemma to use it, right? So we're going to say by exact, we're going to use this, and now we need to fill in a whole bunch of things, right? So unfortunately, we don't have 0 is less than 10 yet, so we have to say by simp, and that should be it. Okay, great, perfect. I think that'll be it for this video. I will try to put this in the standard library. Who knows, maybe they already have it and I didn't notice, or maybe they will want it, and that'd be cool. So that's it for this video. I hope you guys enjoyed.